I'm Bob Duhamel, and today I'm going to answer a question about one of my videos on the nature of ground. And this question comes from the viewer whose name I have up here that I can't pronounce. I apologize. But the gist of the question is, when you're using ground as a matter of safety, how does the current know to go through ground instead of through you? Does it act like some sort of a switch? Well, let's take a look at the circuit in question. And we have just an equivalent circuit, a 110 volt battery that represents the power plant and the generating system and all of that out there that's supplying power to your house. We have a motor, which is an electric drill or some other type of equipment that you're working with. The dotted line represents the metal casing, which is insulated from the wires, of course. And here I am touching that metal casing, and I'm touching the ground. And I have that metal casing grounded also to protect me from a fault inside the drill or whatever I'm working with here. And the ground connects back up to my circuit. This is something I failed to show in the video, but that's important. Thanks for those of you who called me out on this. But that does go back to the circuit to form a return path. It is an important part of the system. Now, the ground isn't special. It just happens to be a very good conductor and ubiquitous. It's all around, so we use that as a return to get back to the circuit and to make a safety connection or a ground to that ground for safety purposes. So we have 110 volts, my motor, my case, it's insulated. I'm touching the case, but I'm safe because I'm insulated from the 110 volts. Everything's going just fine. But what happens if there is a fault? Let's say somehow this gets connected to the case. Some kind of a short circuit, something gets in there, some insulation breaks down, who knows what, maybe some water got in, but I've got a connection there. So the question is, okay, the 110 volts goes to the case, I'm touching the case, the ground is touching the case, we're both connected to 110 volts. How does the current know to go through ground instead of me? Well, the myth is that the current finds the shortest path to ground. And it doesn't work that way. The current doesn't come in and say, there's a high resistance path, there's a low resistance path, I'll take that path. Nothing like that happens. There's no magic involved. It's just another series parallel circuit or another parallel circuit. It has one path here, one path there, and the lion's share of the current is going to go through the lower resistance. But I'm still connected to 110 volts. It is confusing. Why does this protect me? And I think the reason it's confusing is because we're looking at the wrong place. We look at this and we see 110 volts. I'm connected to 110 volts. The ground's connected to 110 volts. What's the difference? Well, we don't want to focus here because the magic goes on over here. When we draw diagrams like this to understand electronics, whether it's looking at Ohm's law, Kirchhoff's laws, or series parallel circuits where we have a battery and some resistors or other components, we always leave out something important that happens in the real world that doesn't happen in our model circuits. And that is over here, we have resistance. If it's a battery, we call it internal resistance. If it's another component or another system, we call it output impedance, but it's always there. So the battery has its own resistance. The generator and wires and transformers and all the stuff that deliver power to your house, they have internal resistance, or we would call that output impedance. We don't want to get into the capacitive reactance and inductive reactance because that's important, but we'll talk about that in alternating current. But we'll just reduce this down to a battery and its internal resistance. So the battery really has resistance of its own. I'm going to put it up here just for illustration purposes. And remember that this is part of the battery. I don't want to clutter it by drawing a dotted line around it or something, but remember this resistance is part of the battery. We can't get rid of it. And everything has this internal resistance or output impedance. So to understand why that makes things safe, let's unclutter this a little bit and just look at what happens. Let's get rid of everything here for now. Let's just put a resistor here. Now let's say this internal resistance, I'm going to make a really high number. Let's make it 10 ohms. It would really be much less than that, but for illustrating purposes, let's just make that 10 ohms. And over here, let's make this 100 ohms. This resistor represents our tool or whatever we're working with, or it could be almost anything. We just want to look at what happens over here. So don't worry about what this is. We want to see what happens over here as we use current from the system. So right now we have 100 ohms, 10 ohms, 110 volts. How much current am I going to get? Well, it's a simple Ohm's law problem. Current's going to travel in that direction. 100 ohms in series with 10 ohms, that's a total of 110 ohms. You just add them together in series. 110 ohms, if you know your voltage, you divide into it. So 110 ohms divided into 110 volts gives us 1 amp. That's reasonable to run a motor. It might even take a little more. So we have 1 amp going through the circuit. But more importantly, what happens to the voltage right here? We have 1 amp going through a 10 ohm resistor. Now what happens when you have current go through a resistor? Whenever you have current going through resistance, you get a backup of voltage. Here's my trusty soda straw I used to illustrate this with. Now if I blow through the straw, I get pretty much the same pressure inside the straw. We talked about how there's actually a pressure gradient, but let's not get too complicated about this. But the important thing is if I pinch that straw off, causing resistance, now I blow into it. That pressure backs up and becomes higher where the current goes into the resistance and is lower after the resistance. So we have a differential of pressure. And remember, any kind of pressure is always measured as a differential, and voltage is electrical pressure. So it's the difference that matters. So I have a higher pressure here and a lower pressure here. So I have the same thing over here. When I push current through a resistance, I get a higher voltage here than I do here. Now this voltage is pretty much locked in at 110 volts because it's locked into the battery voltage. So if I have a higher voltage here and a lower voltage here, I must have exactly that, higher voltage, lower voltage. So my voltage here is something lower than 110 volts. How much lower? We can figure that out by Ohm's law. The difference in voltage here, and remember we're always concerned about the difference in voltage. Voltage is always measured as a differential. What's the difference between these two voltages? I calculate that out with Ohm's law. I have my 1 amp of current, my 10 ohms. If you don't know your voltage, you multiply. So 1 times 10 gives me 10 volts. So I have a 10 volt loss across here. Higher voltage, lower voltage. 110 volts, I lose 10 volts. I'm down to 100 volts. So by taking that 1 amp of current, my voltage has dropped, so I only have 100 volts across my 100 ohm resistor. Is that going to work? Do I still have 1 amp? Of course I do. It always works out. So let's calculate that out just to be sure. 1 amp, 100 ohms. 1 times 100 equals 100. Ohm's law still works. So I have 100 volts across here, 10 volts across there. Also notice that the voltage is distributed proportionally. I have 100 parts of resistance here and 10 parts of resistance there for a total of 110 parts. 100 parts of my voltage and 10 parts of my voltage. It's always proportional to the resistance in a series circuit. So what happens if I reduce this resistance? That's like I have my variable drill, I press the trigger, that reduces the essential resistance or reduces the impedance of the drill. It draws more current, goes faster. So let's make that 50 ohms. Let's make that 45 ohms just to give us an easy number to work with. So I have 45 ohms and 10 ohms. That's 55 ohms total. So 55 divided into 110, that gives us 2 amps of current. So now I have 2 amps. What's going to happen to this voltage here? I have more current flowing through the resistor. More current through the same resistance means a greater voltage. So that means this voltage here will increase. So what does that do? Well, this voltage can't change. This voltage must be higher than that voltage. If the difference got larger, that means I'm losing more voltage. So what happens is I have 2 amps through 10 ohms. Now that becomes 20 volts. So now I start with 110. I lose 20 volts coming to here. So now I'm down to 90 volts. That's the key to what happens later on. The more current I take, the lower this voltage becomes. Now let's reduce this down to 1 ohm and see what happens. That's no longer 90 volts. That's no longer 20. This is no longer 2 amps. So now with 1 ohm, I've got 10 ohms plus 1 ohm. That's 11 ohms total. 11 ohms goes into 110 volts. That gives me 10 amps. So now what happens to my voltage here? I have 10 amps through 10 ohms. If you don't know your voltage, you multiply. So 10 times 10, that's 100 volts. So now I have a huge voltage differential. It's like I'm blowing really hard. Now I get a huge buildup in pressure here compared to the pressure here. And this pressure must be higher than that pressure. And once again, when we relate that to voltage, this voltage has to be higher than that voltage. This voltage is locked in at 110. So if I have a greater voltage here, that means I'm losing more. So I started with 110. I lost 100. What's left over? 10 volts. So now, with this 10 amps, I only have 10 volts left across this 1 ohm resistor. Is that going to work? 10 amps, 1 ohm, does that give me 10 volts? Of course it does. Ohm's law. 10 times 1 gives me 10 volts. So now I only have 10 volts over here. So the lower the resistance is here, the more current I get, and the lower the voltage becomes here. We can look at that other ways too. If I push 10 amps through 1 ohm, how much voltage do I get? Remember, we push current through resistance, we get a backup of voltage. If I push 10 amps through 1 ohm, Ohm's law says I'm going to get a 10 volt backup. So I have a backup of 10 volts across here. So we can look at it multiple ways. So the lower I make that resistance, the lower the voltage across it is going to be. So if we look at this now back at the system we had, so now I have my motor back here, my insulated case, I'm touching it, and my ground connection, let's just say that's 1 ohm. It's too high, but this will show what happens for illustration purposes. So I'm safe now because this case is insulated. I'm not touching the 110 volts. But here comes our fault. Somehow we get a connection there. Now I have the 110 volts going to the case. Now I've got a problem. So, but am I connected to 110 volts here? If I were, I'd get about 50 milliamps through me, which would be deadly. But I'm not going to get 50 milliamps, not because the current comes in and says I'm going to take the shorter path, but this 1 ohm resistance combined with this 10 ohms gives us a total of 11 ohms. 11 ohms and 110 volts gives me a current of 10 amps. Now here comes the magic. Nothing going on here is doing anything special other than the fact that this 1 ohm resistor causes my total resistance to be so low that I'm getting 10 amps through the system. The magic is happening because that 10 amps is going through this 10 ohms here. Where's that 10 ohms? That's out in your generators and your transformers and delivery system, all the wires. That's inherent in the system. We can't get rid of it. So that wire coming into your house, looking into it, you see 10 ohms of resistance. But that 10 amps has to come through that resistance. So what happens? 10 amps coming through 10 ohms. I'm going to develop 100 volts across that. So I start with 100 volts, I start with 110 volts, I lose 100, leaving me with 10 volts here, and now I've only got 10 volts across me. So this isn't some kind of a current attractor, it just lowers my entire impedance. Remember, I've got, who knows, maybe it's a hot, humid day, I'm sweating, I've got really good contact with the case and the ground, and all the factors add up to about 2K. So how much current am I going to get through me? Well, 10 volts, 2K, I'm going to get through me about 5 milliamps. Well, that's not enough to be dangerous. So it's the fact that my voltage is down to 10 volts that makes me safe. So once again, this is not some special current attractor here. Together, we have a resistance of about 1 ohm. Remember, resistors in parallel. How do you do that? Well, we could say, well, 1 times 2 divided by 1 plus 2. Now we don't need to do that because we know that our total resistance will be lower than our lowest resistance. So 2K in parallel with 1 ohm is going to be just a little bit under 1 ohm. So we're essentially 1 ohm, 10 ohms, total of 11 ohms. So this lowers our total resistance down to 1 ohm, gives the whole system a total resistance of 11 ohms. That gives us our 10 amps. That's the magic. Getting that 10 amps to come through this inherent resistance causes a 100 volt drop, and now I only have 10 volts across here, which is fairly safe. Now in the real world, this might be more like a thousandth of an ohm. What's that going to do? Well, that's going to, with 10 ohms, that's going to max us out at about 11 amps. That's the best we're going to get, because that's going to be essentially nothing in 10 ohms. So we have 10 ohms, 110 volts, 11 amps, and so I've got 11 amps, but it's not coming in and saying, I'm going to go through the low resistance. No, we've got basically 0 volts. So this very low resistance causes so much current to flow through this resistance that it drops my voltage down to nothing. I lose all 110 of my volts there. Once again, 11 amps, 10 ohms, 11 times 10 gives me 110 volts. I start with 110, I lose 110. I'm down to 0. So that ground doesn't protect me by attracting the current. That ground protects me by pulling so much current through this resistance that it pulls the voltage down to nothing. And now I'm safe. And 11 amps, that's well below what would blow a circuit breaker in this particular example. So I can be pulling that 11 amps till the cows come home and it's not going to blow my breaker. But I'm safe. Why? Because I lose all of my voltage across here. So that's why grounding makes things safe. It's not some kind of a current attractor that attracts the current through the ground. I've still got, well, I only have 0 volts here, so I have no current through me. And essentially 0 volts across essentially 0 ohms, I get practically 0 volts across it. So that's the way it works. Once again, just quick emphasis, I don't get saved because of the myth that electricity seeks the shortest path. I get saved because my total resistance, me and the ground, becomes so low that I get so much current through here. Here's where the magic happens. I pull so much current through this resistance, which is out in the system, we can't get rid of it, that I lose all of my voltage across there. Simple Ohm's law. I take current through a resistor, I lose voltage, and with 11 amps, I lose all my voltage. I have nothing left here to be dangerous. So I can hold that all day long and wouldn't even know it. My drill wouldn't be working because who knows how much resistance it has. It's going to only have, well, it's going to have 0 volts across it too. So why is my drill not working? Why is the wire getting hot? So that would protect me though. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.